We are going to discuss today. And the first problem is this one. It says, given any 4 points on a plane such that no 3 are on the same straight line, what is the maximum number of acute angled triangles possible with vertices amongst these given points? So what we've got here is 4 points, and no 3 are in the same straight line. So I'm just drawing 4 points here. Now, you want to draw a triangle whose vertices are on these points. So that means 3 vertices will be occupied and 1 vertex will be left out. So if you want to draw all the possible triangles, all you have to do is to leave out 1 vertex. Suppose I leave out this vertex, and then the triangle that we have here is this one. All right. So if we leave out this vertex, this one here, then the triangle that we have is that one. And if you leave out this vertex here, then the other 3 points form this triangle which I'm drawing now. That one, that one, that one. Right? And finally, if I leave out this vertex, okay, the triangle is already there. So you've got the 4 triangles, and the 4 triangles can be identified by the vertices being left out. I think maybe just to identify what those triangles are, I can try to I can try to darken those 4 vertices so you'll know which triangles we've got. Okay, so now the question is now, what's the largest number of triangles you can draw with these vertices? The largest number of acute angle triangles. Now, if you look at this picture here, you can see this triangle here. When I'm pointing there, it means the other 3 points, namely that. You can see it's an obtuse angle triangle. So that one is not counted. If you take this one, then the triangle that obtains when this is left out is that one. And that looks like an acute angle triangle. So that's 1. And then if I take this one, I do have an acute angle triangle, 3. And then if I take this one, I got an obtuse angle triangle. So in this particular picture, I've got 2 acute angle triangles. Now, I actually can draw a situation where I got 3 acute angle triangles. And one can try to construct it. It took me a while, but I noticed that if you draw a kite, I think I can draw a kite with certain angles. I'm not sure what these angles were, but I think if this is 42, I remember taking 42 as one of them. And now in a kite, the diagonals cross each other at right angles. So if you got this as 42, oh, now this This is obtuse angle, obviously. Okay, look, the diagonal is not, it's not accurate. So we can make this 42, 42, 42, 42. This angle this whole angle is supposed to be 84. Sorry about this. And so this will be 50. I think it's 58 and 42. I'm sorry. Look, I must apologize. I can't remember exactly what it is, but you can actually construct this. I think you can an 84 and an 84, and these are two equal, and they add up to 168. So the other ones will add up to 92. So these two angles will add up to 92. So you'll have something. All right. Just try out some numbers here, but there is a kite where those three, this top triangle and this bottom triangle, and another one are equilateral. So I mean acute angles. So I think yeah, it's going to be like that, like that, and there's a, so you got an acute angle here. I think this becomes obtuse, and these are the same here. Both these angles are acute. This is also acute, and the only one that is obtuse is this one here. So that way you will have three acute angle triangles. Try to do that. I'm sorry, I can't remember the actual figures, but I was playing around and I was able to do that. Okay, so it is possible to get three acute angle triangles. That is the lesson that I am trying to convey here. But now, is it possible that all four triangles are acute angles? So that is the question. Is it possible that we said three you can get three acute angle triangles, but they want the maximum number. So the only other way is where you get the all four angles are acute. All four triangles are acute. Now the point to notice here is that in each of those four triangles, that is an angle of one of the triangles. This is an angle of one of the triangles. This is an angle of one of the triangles. And this is an angle of one of the triangles. So since all of them are acute angles, it means that those four ones which are marked here are all acute, which means that each of them is less than 90 degrees because they're all acute. Now, if that is the case, then the sum of these four will be vertex angles is less than 360. If this is a condition, if all four triangles are acute angles, acute angle triangles, then you will have that the four vertices, or the four vertices, all vertices are acute because each vertex is in one of those four triangles, which will mean that the sum of the vertex angles is less than 360, but that is impossible because the sum of those four vertex angle is actually equal to 360. Contradiction. Because sum equals 360. Okay, so that's the first problem. So the answer is 3. You can have 3, but you can't have 4. So then the maximum number of acute angle triangles is 4. Okay, so that's the first problem. Let me get on to the next problem. All right, so the next problem is the lengths of two sides of a triangle are 200 centimeters and 150 centimeters. The length of the third side is also an integer, right? Like these two are integers. Now, what is the minimum perimeter in centimeters of the triangle? In other words, if you've got two sides of a triangle, there could be many, many triangles that you can construct, right? So let's have a look at this problem. If you've got two sides, one is 200, sorry. So you got two sides of a triangle. So you got a 200 and 150, right? And so the third side can be this. Now the 150 can be anywhere. You could have a 150 down here. You could have a 150 this way like that. We could have 150 up there. So all these 150s will lie on a circle, all these points, and this is 200. Let me just put this down. This is 200. And the 150 could be any one of these. Now the question is, of all these possible triangles, which one has got a minimum perimeter? So that's really the question. So we need to draw a, so the perimeter here will be adding those three, or you can add these three, or you can add those three. I could add those three. There are different perimeters. So you want to know which of these has got the smallest possible perimeter. Now, how do you do that? How do you find this? It doesn't look easy, but there's very important thing which we have discussed before. I can't remember all the things that I had discussed, but I'm sure we had discussed this, that the sum of two sides of a triangle is always greater than the third side. Okay, if you add two sides of a triangle, then the sum is always greater. So you got a 200 and you got a 150, and say the third side is x. So these third sides are the red lines here. Okay, so now we have that the sum of two sides of a triangle is greater than the third. So let's have a look at that. X plus 150 is greater than 200, right? If I put 200 on the right-hand side, I can put 150 on the right-hand side, or I can put x on the right-hand side. And in this case, I'll have x plus 200. And here I will have 200 plus 150. So you have three inequalities, right? Now, one of these inequalities is obvious, like this one here, x plus 200 is certainly greater than 200 plus some number is bigger than 150. So we can rule this one out because this is of no assistance. But this one here can be useful because if you bring the 200 to the other side, then you have 200 minus 150. So x has to be greater than 50. The 50 plus 150 is 200, but anything bigger than 50 will make this true. So in the first place, you got x is greater than 250. And in the other case, the person whose name is given as Samsung SM, please switch your mic off. And this one here says that x is smaller than 350. So now we have restrictions for the third side, x. In the one hand, it must be greater than 50, and on the other hand, it's smaller than 350, right? And it's an integer. So what are the possible values for x? So it must be an integer. The first integer greater than 50 is 51 and goes all the way. And the last integer less than 350 is 349. So these are the possible values for x. So the question is now, what are the, how many triangles do you have? So you will have as many triangles as there are numbers in this sequence. And I think I'm at some point I told you how to count the numbers in a sequence like this. There's a formula for that, but with consecutive numbers it's easy. All you have to do is to take the last number, subtract the smallest one, and add 1. So you will have 349 minus 50, which gives you 299. There seems to be something wrong here. I don't remember this particular answer. Oh yeah. Yeah. No, we want the minimum perimeter. So the perimeter is, these are the values for x, but the question is not what is the minimum value for the third side. The question is, what is the minimum perimeter? The perimeter of this triangle is the sum of the 3 sides. So that is x plus 350, right? And the smallest possible value, this is the smallest minimum perimeter, the smallest is the smallest value of this. And that tells you must get the smallest value for x, which is 51. So we didn't need to know all those things. Smallest value for smallest, or the minimum, equals 51 plus 350, which is 401. So that's the minimum perimeter. Okay, so I actually wasted a lot of time. I could have said the smallest value for x satisfying these two conditions is 51, and that will have given my answer. So my error in this, in trying to solve this problem, was that I did not ask myself, what is the goal? I told you, always find the goal. So the goal here is, what is the minimum perimeter? And we should have started off by saying the minimum perimeter is that. That should have been the first sentence, right? And then we say, okay, that means I need to find the smallest value of x. And then you do all this, and then you will see the smallest value of x, which is bigger than 50 and less than 350, is 51. And that will give you the minimum perimeter, 51 plus 350. So that is how I should approach the problem. And anyway, it's a good learning experience. It shows that I could have done it in a much better way. Okay, so let's go on to the third question. The square ABCD has sides of length 6 units. It's a square. Yeah? So let's draw a square having the sides 6 units. That looks like it. Let me get back to my black. Okay, so all the sides are equal to 6. It's a square. So that's the first sentence. So the question is now, we'll just bear that in mind. M is the midpoint of AB. Okay, let's just put down. P is a variable point on BC. So you got A, B, C, D. And M is the midpoint of AB. So we'll have M. It's a midpoint. So this is 3. And this is 3 because all the sides are 6. And this is the middle point. Now, P is a variable point on BC. So you have P is any point on this line. Okay. Now, find the smallest value of DP plus PM. So I'm going to choose a random point on this. Let me just choose blue as my color. I'm going to choose P could be a random point, and dp is that one. You want to add dp to pm. So now the question is, as p varies along this line here, there will be lots of possible values for dp plus pm. If p is here, you get dp plus pm. P is there, dp plus pm. What is the smallest possible value? Okay, so this looks like a quite a tricky kind of a problem. How would you solve this? Okay. Now, usually in a case like this, what happens is you use the fact that the straight line is the shortest distance between 2 points. Right. Now, you don't have a straight line here. I'd like to have a straight line dpm. So I can say, if that is a straight line, then it's then that will be the shortest distance. So how do I do that now? The way to do that is actually I joined the wrong thing here. I'm sorry about this. Let me just, I should have joined the midpoint. The midpoint was here. Right. So this length here is 3. So to get this thing in a straight line, it's a common trick. If you don't know it, then you'll never be able to guess it. But this is the way you do it. What you do is you kind of take this line here and reflect it on the across BC, reflect it across. So then you will have something where you can put those 3 things in the same straight line. So to reflect it, what we mean is I draw something like this. Okay. And then when I'm reflecting it, what happens is you've got, this is still 3. MB is 3. And this part here will also be 3. And now P is a variable point. So I could have had, once I got this point here, now, if you look at these 2 triangles, there's 90 degrees here, right? And if you take M and you reflect it on the other side, so this is 3 and this is still 3 here now. So these 2 sides are the same. These 2 are 90 degrees and this is a common side. So it means that these two triangles are congruent. So PM, which is under investigation, is the same as that one. So if I put M and translate it to this side, let's call that M prime, then we got this thing here, the dP plus PM is the same as dP plus PM prime, because these 2 triangles are congruent. And now you want this to be as small as possible. Okay, so if I take various choices for P, I could have taken P to be here, in which case dP plus PM prime is that sum. Or I could have chosen it here, in which case dP plus PM prime is the sum of those 2 lines. Right. And you will notice that the sum of these 2 is always greater than the straight line that joins these 2, because we just said in the previous one that if you have a right angle, a triangle, the sum of two sides of a triangle is always greater than the third. So I could have had to draw the straight line that joins dp and m prime. It's rather squeezed in here, right? All these sums, dp plus pm prime, is always greater than dm prime, the straight line. So this is always greater than dm prime, right? So what we need to do is draw the straight line and say the point P that we're looking for is that one, because that one will give you the shortest possible sum, right? All the other ones are, in all the other cases, you got the sum of two sides of a triangle, which is greater than the third side. So the shortest line, another way of looking at it is the shortest line between 2 points is the straight line. Okay, so we've got the point P now. The question is now, what is the value of dm prime? So dm prime is the minimum value. But now we need to calculate what that dm prime is. Okay, so what I'm going to do is I'm just going to just knock off these blue lines here, and then I'm going to look at, we need to look at dm prime. So we've got this dm prime and a, they form a right angle triangle. So dm prime is a hypotenuse of the right angle triangle, which is great because we can calculate. Remember, this was 6. So you got 3 here, you got 3 here, you got 3 here. So this whole thing here is 9, right? So the dm prime is the hypotenuse of this right angle triangle, and that can be calculated. So dm prime is equal to the square root of 6 squared plus 9 squared. Right? Those are the other two sides of the right angle triangle, and that is the same as square root of 117, 81 plus 36. So that is the smallest possible value of dpm plus pm. Interesting problem, right? But the trick is that you can't work out the minimum as it stands. But if you take it across, then suddenly the whole thing becomes alive, because you know that the sum of two sides of a triangle is greater than the third. Okay, so that takes care of that problem. And I need to get to the next problem. Okay, I just want to take a quick break here and say hello to all you guys.
Hello?
Yeah, okay, so hi everybody. I'm glad some people came back here. I went away because we were starting late, but you came back. You might have missed a few things. My apologies for that, but I think it will be put on YouTube. David, I tried to look for these talks on YouTube. I think the way to do that is you first get into YouTube, isn't it? It's not in the SAMF website. You have to get into YouTube and then.
No, but I do have the link for the SAMF YouTube. I did share to all the learners on the document.
Oh, I see. So they can get, okay, they can get directly to that.
The link is there, yes.
Okay. So that's great.
Okay.
All right. Okay, so in case you missed out some of those early solutions, you can go into YouTube. Everything is recorded, and you can catch up on that. Okay, so I just want to say hi to everybody. Some people have come in late, and welcome to the whole class. Okay, now the next problem is this one. Let's have a look to see what's going on here. In the acute angle triangle ABC, I've drawn the triangle. BC is AB plus 1. AB plus 1 is BC. So this BC here is 1 more than AB. So let's just call this thing, say, maybe C. Normally we call the side opposite angle C, we call it small c. And okay, so BC is AB plus 1. So if this is C, then this is C plus 1. Right. Then you also have that AC is BC plus 1. All right, so we already got BC is C plus 1. So AC is C plus 2. Right? Okay. Right. Now you also have that AD is perpendicular. And the question is find CD minus BD. Okay, so how do you do that? Well, we don't know what BD and DC is. Let's just call it X and Y. I can call it X and C plus 1 minus X, but that looks too complicated when you got 3 sums. You know, it's hard to do algebra with that. So let's just call it X and Y. And then just bear in mind that X plus Y is C plus 1. That's a much neater kind of a thing. If I need not have called this Y, I could have called it C plus 1 minus X because they both add up to C plus 1. But it looks rather messy to do it like that. Okay, now the question is find CD minus BD. So in other words, what is Y minus X? It's Y minus X. C is not given. And X and Y are also not given. So it's, how do you do this? Obviously, we need to get the assistance of algebra. Right? So you got Y minus X. Now, one of the things I can notice here is that you got 2 right angle triangles, and in each of these right angle triangles, I got 2 sides. Okay, I've named them. You got CX and C and X, and here you got C plus 2 and Y. So I got 2 sides in each of these triangles. So the third side can be calculated. So let's just put AD squared. If I look at the left-hand triangle, that's equal to C squared minus X squared. C squared minus X squared. Right. But that's also equal to AD squared is also equal to C plus 2 all squared minus Y squared. Because C plus 2 is the hypotenuse of this right angle triangle. And we're looking at AD squared. So by Pythagoras, you've got AD belongs to 2 right angle triangles, and you've got this equation. And now if you look at this, you see you got the Y minus X, which we are trying to get, is somehow inside here, because if I bring the Y squared on this side, I got Y squared minus X squared, you see. And that is related to Y minus X. Y squared, bring it to this side, and this side you will have C plus 2 all squared minus C squared. So if you bring the C squared to this side, Y minus. So, okay, now this factorizes. This is Y minus X into Y plus X. We need to find out what this is. All right, so we got on the left-hand side, we zoned in on this quantity that you're looking for. Now let's see what happens here. You got this is C squared plus 4C, it's the square of a binomial, plus 4 minus C squared. So you got Y minus X into Y plus X. This simplifies a little bit. The C squared minus C squared, and you have 4C plus 4. And 4c plus 4 is 4 into c plus 1. And lo and behold, c plus 1 is also x plus y. So very nice. C plus 1 is the same as x plus y. So why is it very nice? Then I can get rid of the x plus y. I can cancel these. Oh, this is 4 into x plus y. So I can cancel the 2x plus y's. I can't cancel, it's not 0, obviously. You can't have the sum of these two things equal to 0. Otherwise, you have got a triangle with 0 side, which is impossible. So when you cancel, you get y minus x equals 4. Right, that's very nice. Okay, so the method to do this is to start with this. You see, you got BC is AB plus 1. So I've given a name to AB. And then the moment I got that, then I moved in slowly from that to that to that. And I only have one unknown, C. And then I called these some names. And eventually that allowed me to say what the goal is, to work out y minus x. And the rest of it is algebra. Okay, it's a nice problem. I hope you enjoyed the solution to that one. I'm not sure whether you tried these problems. Let me just ask a question here. Okay, how many of you actually have tried these problems? If you have, just put your hands up. There is a little thing. Okay, I can't see who's putting their hands up. But hopefully you guys are tackling these problems before you come to this class. I've told you in the first two classes, I said it's a waste of time coming and looking at answers without knowing what the questions are. You don't do mathematics just knowing the answers without knowing what the questions are. So hopefully I have trust that you all have tried this problem. I also want to congratulate those people who have taken part in the team competition. I was very pleased to see that the senior teams from our centers, they did it quite well, considering that there were 43 or 42 teams taking part, and the 3 teams that were fielded from our side came 5th, 6th, and 7th. So you can give yourself a pat on the back for doing so well. To come in the top 10, all 3 teams, I was very pleased with the result. Okay, so let's just get on to the next problem, which is so the next problem is this one here. In the diagram shows quadrilateral PQRS with PQ parallel to SR. So let's just record that. It's parallel. And 3 sides are given, right? It's in the picture. So those are the information there. Now we've got the picture. The 2 triangles PQRS. Oh, I got a way of finding everybody. Okay. All right, now I can see the whole screen. How many of you tackled the problems before coming to the class? Put your hands up. Nobody. Nobody. Oh, Hayden did, seems to me. Answer. Okay, so there are some people who have tackled it. We can do better. Okay. All right. So let's just get back to my screen now. No, what happened here? Sorry, I'm serious. I seem to be having some problems navigating this kind of a thing. Let's just stop the share and start all over again. Senior session. Okay, that's better. Okay, so can you see it now? Can you see the screen now?
Yes, Prof.
All right. Okay. Now the two triangles are similar. Now this is very, very important. It means that the two triangles have the same angles. Now, some of you are in grade 8, and in later grades, I think grade 9 or grade 10, they do what they call similar triangles. Let me just tell you something about similar triangles. They're very interesting parts of geometry which deal with a section called similar triangles. You see, you have triangles which are congruent, which means that they are equal in every respect. And then one of the conditions of congruency which is glaringly absent is where the three angles of a triangle are the same, or two triangles are the same. You can have three angles all equal to each other, but they need not be congruent. As you can see in my diagram, I can draw two triangles which are got the same angles. This is x, x, y, y, z, z, but they are not congruent. Right? The one is, if you want, you can say it's a photograph of the other. Right? Then you get a smaller version. Right? So these two triangles are not congruent, but they are said to be similar. They are similar if they have the same angles. If the angles of the one triangle are the same as the angles of the other triangle. So there are the most important theorem regarding similarity is that the sides are in proportion. What that means is that if these sides were, for instance, 3, 4, and 6, and this was 30, then you can say this 30 here is 10 times 3, and all the other sides will be 10 times. The next one will be 10 times 4, and the next one will be 10 times 6. If you know one side, then the other two you can calculate it because they are in the same proportion. In other words, 30 over 3 is 40 over 4 is 60 over 6. Why did I say this? I'm saying that if I named these sides as A, B, and C, and P, Q, and R, then we could have had, instead of having these numbers here, and these triangles are similar, then you can conclude that if the sides are A, B, and C, and say P, Q, and R, then A over P equals B over Q equals C over R. C over R. So the ratios of the sides are the same. That is why we say they're in the same proportion. But if you know, in other words, if you multiply A by something, if I multiplied A by something to get to this, say I call this AX, then this one here will be BX, and this will be CX. You have to multiply everything by the same quantity, right? So they're in the same proportion. Each side is multiplied by the same number. And conversely, if you got two triangles like that where the sides are in proportion, then you can prove that these angles are the same. Very interesting. You can prove that those angles are the same if you know that the sides are in proportion. All right. So that you will do in some detail when you do at some point in your geometry class. But what I just told you now is the most significant thing about that. One useful thing is, like, when you have a triangle, and you have a line parallel, a parallel segment where the two ends are on two sides, like the way I've drawn, then there are two triangles. The two triangles are this triangle there and the large one, but they have the same angles because parallel lines means that the corresponding angles are equal. So if this is x, that is also x, and this is y, this is also y. So the large triangle, the angles are x, y, and z, and the small triangle, the angles are also x, y, and z. All right. Mogi, I'm in the class. I'll call you later. Okay. Okay, so you have, these are similar triangles. So these two triangles are similar, which immediately tells you that you got some ratios which work in this, right? When you calculate all those ratios and so on, from there you also get a nice result that the ratio of this is to this piece is the same as this is to this piece, right? This over this equals that over that. Actually, you'll have that this over the whole thing equals this over the whole thing, because this is a side in the small triangle, and this is a side in the large triangle. So this sides are in proportion. This, which is opposite angle y, is over the whole thing, which is opposite y in the large triangle. So that this piece over the whole piece is the same as that over the whole piece. So that's also a useful thing. I had to tell you that because we need to we'll be using that just now to solve this problem. The two triangles are similar. So I went on to this little discourse about similar. If PQRS is not a parallelogram, what is its perimeter? Okay, so that's an interesting thing. I don't have too much of time, so hopefully you'll stay with me till the end. We started late, so okay. So we don't know what the perimeter is. We got two sides, and I'm given names to those other two sides. So the problem is to calculate that. What is the perimeter? What is 4 plus 5 plus b plus a? All right. But we know that they are similar, you see. That's a powerful fact. Okay. Now, it's given that PQ is parallel to SR. So immediately, you got these two lines are parallel, and that tells me that that angle equals that angle there, because these are alternate angles. All right, so we know the two triangles are similar, so at least we know that this angle is equal to this angle. Now, the problem is now, what is this angle equal to? It's going to be equal to one of these other two angles, but which one? So that becomes a dilemma. See? Okay, let's try this angle. Let's call this angle your y, right? Now y is going to be equal to either that or that. Now think about this. Is it possible for y to be equal to this one? Can this be equal to this? Right, I'm sure some of you, unfortunately, we don't have a one-to-one discourse here, but I'm sure you realize that if they were equal, then it means that PS is parallel to QR, because these are alternate angles, right? But then we already know that the other pair is parallel. That will force this thing to be a parallelogram. And it's clearly said that this is not a parallelogram. So we can conclude that this angle is not y. If it is y, then you have a contradiction, because you can conclude that this is a parallelogram, which is false. So this y here is not equal to that one, but because they are similar, y is certainly equal to one of the angles, and it has to be this one. Right. So now we've got x and y in this triangle, x and y. And because all the three angles add up to 180, the third angle will have to be the same. So now we've got these triangles are similar. You can see they've got the same angles, right? And therefore now we can use our, the sides are in proportion. Now, watch carefully. You know, I think at some point or the other, I told you that when you have in a triangle, the sides are come in pairs. That is associated with that. This is associated with the side opposite it, and that one is associated with the side opposite it. So in similar triangle, this fact becomes very, very important, because when you say that the ratios are the same, you have to know which sides of one triangle are in the same ratio as which side of the other triangle. So let's take, like for instance, I take 4, which is in the top triangle. We call this top and bottom. The 4 over one of these sides. Now, which side here corresponds to 4? Now, the way to do that is, it's going to be one of these sides, but 4 over what? Now, 4 is matched with x. Listen very carefully to this, because this will certainly help you when you are doing metric geometry. 4 is associated with x. So now you look at the next triangle and see which side is associated with x. The side which is associated with x is b. So 4 over b is what you've got. So let's try 5 now. 5 is associated with y. Now in the other triangle, what is associated with y? Y is associated with 7. So you have 5 over 7. And then finally, you got z. Now you got 4, 5, and the third side is 7. 7 is opposite z. And in this other triangle, what is opposite z? A. So you got some nice, beautiful equations coming out here. And that allows you to calculate A and B, because these, it's a nice little equation here with only one unknown. So you got 5b is equal to 28. When you cross multiply. And here, you got 5a is 49. Cross multiply, 5a is 49. So we need to calculate a plus b. Well, I can add these two, and I get 5 into a plus b is 28 plus 49, which is 77. So a plus b is there, 77 over 5. Right? So you've got our a plus b. So once you've got a plus b, you got, say this is equal to 9 plus 77 over 5, and etc. So that gives you the perimeter. The question was, what is the perimeter? So I did the right thing this time by asking, what is the problem? And I wrote down that problem right at the beginning. And then I realized I have to calculate a plus b. And the rest of it followed because of similar triangles. Okay. All right. So that is a good, very nice application of similar triangles. The next problem is, so this is your assignment. Right, this week's assignment, session 7, number 9. So it's an interesting problem. It looks quite easy. And you're asked to calculate an angle, CAM. And the wonderful thing about this is that not a single angle is given. But yet you can calculate the angle CAM. It's a very interesting problem. You say, how can you calculate this angle with not a single angle is given? But you've got a circle, some important facts here. This M is the center. So AB is the diameter. Right? And you got lots of radii, MA, MC, MD, MB, right? And when you got that, you got lots of isosceles triangles. So the grade 8 students or the grade 10 students will have to use isosceles triangles and so on to eventually get to the answer, and you can do it. But some other people who know some little bit of circle geometry, they'll be able to find it a little bit, find the answer a little bit faster. Okay, so I'm not going to say too much about that. That is your assignment, a very interesting assignment. I wish you luck and good wishes to solve that problem. Okay, so now let's just go on to the next one. Two vertical sticks in the ground have lengths 2 meters and 3 minutes. Okay, so you've got a picture here. This is supposed to be the ground, and you've got a vertical stick, 90 degrees. Let's just record that. They're vertical. The top of each stick is joined to the bottom of the other by means of two strings. The string is joined here. This is another string. And the strings meet at this point P. What is the height of P above the ground? So you need to work out the height of P So I need to work out this red line. This is the height, perpendicular height. I found this very interesting because all you're told is that these two sticks are just stuck into the ground. You get the feeling that if the sticks are very far apart, then the height gets smaller. Because if I make this stick some place which is quite far away, up there somewhere, I put the second stick here, 3 meters. And now if I join this and join that, your intuition tells you that the P is going to be weighted down. It'll come smaller, it'll come closer to the ground. So it looks as if the problem cannot be solved because you've got this thing. They don't tell you what this distance between these two poles are. But curiously, it doesn't really matter. No matter how far the stick is, P is always at the same height above the ground. And now that is the power of geometry and the power of mathematics. See? All right, so what I'm going to do is I'm going to put some symbols here. I'm going to use A here, and I'm going to use B here, right? And I observe that I have a triangle, a right angle triangle, like this. Let me just isolate this triangle here. This one. I got a 2 there. Oh, sorry. I got a 2 here. And this is A plus B. And then I got a height here. Let's call this H for height. Right. Now, earlier, I told you that when you have a triangle and you got a parallel line, then you got two similar triangles. That one is similar. I call this the baby triangle, is similar to its mother, the large triangle. In this case here, the baby triangle is that one, and the mother is the big triangle. So you got H, it's there like that. This is the H, and then, and this triangle is similar to the big one. So you'll have that H over 2. Let's just eliminate so if I'm looking at these two triangles here, I got that which is opposite. You see, these angles are equal. let's put colors so that you can see it a little bit better. I'm going to put a red dot here, and then I'm going to put a black dot here, and then I got 90 degrees as the third one. So you got the big triangle has got red, black, 90. The small triangle, okay, this is dot now because these lines are parallel, you see? These are corresponding angles. So you can see which angles are common. You got H, which is opposite red, over 2, which is opposite red, the big triangle, right, is the same as B, which is opposite black. And in the large triangle, it's A plus B, which is opposite black, the whole thing. So you got H over 2 is equal to B over A plus B. Right? That is if you look at the left-hand triangle. When I say left-hand triangle, I'm talking about the triangle with this as vertex. But now I can do the same thing with the right-hand triangle. Now if you focus your attention or you move your attention to this right-angle triangle, there you got exactly the same kind of a thing. You got this is perpendicular, so it's parallel to this. And you got this triangle here, and you got this baby triangle here. Is similar to that large triangle. So this time you'll have H over 3. H over 3 is now equal to A over A plus B. Because in this triangle here, you have A is one of the sides, and it's over the corresponding side, the large triangle, which is A plus B. So you got these two equations. And the problem is to find H. And you got 3 unknowns, 2 equations. So how do you do it? The trick is to see that when you add these 2, I'm going to get 1. Beautiful. H over 2 plus H over 3. Same denominator is A plus B over A plus B. Goodbye, A plus B, A and B, bad guys. So that gives you a single equation with 1 unknown. I'm not going to do this. You guys can do this. It turns out it's 1,2 meters. So that's interesting that this height here is always the same. It's always 1,2 meters, no matter how far apart these poles are. I found that very intriguing when I first saw it, because it shows you the power of mathematics. You know, your intuitive can be quite deceptive, but the mathematics doesn't lie. So then we go on to the next problem. See again, these are nice similar triangles problems, which is you guys are all the senior guys. So we are doing some interesting similar triangle problems, and hopefully when you come to this, you will enjoy it very much and you will know much more. So now we're looking at this next problem here. The figure shows quadrilateral ABCD, and everything is there. All those lines are parallel, as you can see, and those 2 are there. And the question is, they say here that AC and BD, the diagonals, are equal. And it's given what they are equal to. It's 56. Okay, so what is the area of ABZ? Oh, that's very interesting, because hardly anything is given here. You got 30, 50. No, we don't have any heights or anything like that. But evidently, we need to find the height. You got the base. ABZ is this triangle here. So we need to find the height of this little triangle here. So how do we do that? Using all this information. Well, once again, similar triangles comes to the rescue. Similar triangles are very powerful. It's a very powerful geometrical tool. Okay, now let's see. You got parallel lines. So therefore, straight away you got angles which are equal here. So you can put, you can see this angle here is the same as this, alternate angles, and these are also equal. So you got this triangle here is similar to this triangle. Obviously, these two angles are equal. They are vertically opposite. Or for that matter, if two angles of one triangle are equal to two angles of the other, the third angle must automatically be equal because they all add up to the same thing. They all have to 180. So if these two angles are equal to two angles here, the third angle will be, to calculate it, you have to add these and subtract from 180, and you do exactly the same for this. So the third angles will have to be equal. All right, so these triangles are, now, therefore they are similar. I'm going to call this thing here, I'm going to call it K, AZ, and I'm going to call this L. Right? So once I do that, now I know that this triangle is similar to this triangle here. So I have that K over ZC. Now K is opposite X and ZC is opposite X. That is why I got K over ZC is equal to, I'm going to put 30. Because I already know one side of this top triangle. That is opposite the remaining angle. And that is the angle here, the one which is opposite, that is 54. So 54, sorry. 6 is a common factor here, so you get 5 over 9. So K, we want ZC. ZC is a subject, if you make it the subject of the formula, you will see it's 9 over 5 times K. So this part here is 9 over 5 times K. So this is 9 over 5 times that. This is 9 over 5 times that. You can check that thing out. 5 goes into 6 times. 9 over 5 is 9 times 6, 54, which is that. And therefore, this part here will also be 9 over 5 times L now. See? Okay. So now, what we've got here is we've called these two things K and L, and using similarity, right? We saw what the sides of this are. So now we've got this whole thing. Now, we also know that AC is equal to BD, you see? It was given. I can calculate AC. Right. What is AC? AC is YK plus 9 over 5 times K. K plus 9 over 5 times K. That is your AC. And the same with BD will be L plus 9 over 5 times L. This plus that. And they're all equal to 56. Right. Now, if you look at this, now you'll see there's something quite interesting here. Because I can take K out. And the remaining factor is 1 plus 9 over 5. I can take L out. And this 1 plus 9 over 5 cancels, which means that K is equal to L. K is equal to L, which is very interesting. It means now that these two are equal. That means this is an isosceles triangle. Interesting that the diagonals are equal. If the diagonals are equal, then it turns out that these two become isosceles triangles. Even this two, because K equals L, you see. So these sides will be the same. Okay, but not only that, because you have this equation 56, yeah? So you have that K so you can calculate K, because K, if you take that into 1 plus 9 over 5, all this is equal to 56. Now 1 plus 9 over 5 is 14 over 5. So you got K times 14 over 5 is equal to 56. And 14 goes into 56 4 times. So you'll get K is actually equal to 20. Right? You can calculate this. Because you've got one equation, one unknown, and L will also be equal to 20. So you got that K, we've actually calculate the precise value. We've got the sides of this triangle. They both are equal to 20. So now that's very interesting. So now we've got an isosceles triangle here, and we've got the three sides. So is it possible to find the area? So that's the problem, is to find the area. So how do you find the area of an isosceles triangle where the sides are known? Okay. The way to do this is, it's quite easy. I'm going to just isolate that triangle whose area I want to calculate. I've got 20 here, I've got another 20 here, and I've got 30 here. So I need to find the area of this triangle whose sides are 20, 20, and 30. So what is the area? The area is half base times height. And half base is fine. There's 15. But what is the height? Now, I've said this thing before. One of the early classes that I had was, I said that when you take an isosceles triangle, you can split it down the middle and you have exactly the same triangle on both sides. Right. So this height here, when you got this height, you actually have a right angle triangle here. See? You have this situation, and these are equal. When you take an isosceles triangle, you split it down the middle, you got a right angle triangle. Now there you can calculate the height, because now you got a right angle triangle, two of whose sides are given. So h squared is equal to 20 squared minus 15 squared. That is using Pythagoras. And that gives you 175. So that gives you the height. You can calculate h, you can calculate what it is, and the area is h times 15. Half base. Half the base is 15 times h. Right, so you got the area. I'm not going to go into the details of that. The rest of it is just routine. So that is the way you do this. So it's a rather longish problem, but you start with similar triangles, and you observe that when you use similar triangles, then suddenly you see that these two angles are the same. Well, actually, these two sides are the same. And that is a great plus, because that makes it into an isosceles triangle. And if you got an isosceles triangle, it's very easy to find the area of an isosceles triangle, because you can split it down the middle, and you have two congruent right angle triangles. Right? We've said this at some other time, which is a very useful fact to have, to know. Okay, how far am I from the end of this thing? Oh, okay. Actually, we just got one more. And I added this thing in case we had time. But unfortunately, we don't have the time. But I will do that anyway. If some people will stay around, they can do it. Now, number 13. So we only got two more problems. This is the second last problem, and I'm going to go on. If some of you want to leave, I think some people have already left. you're quite free to leave because the promise was we're going to finish at 6:30. We started late, so we have a problem. Yeah, it's a very interesting practical problem here. A certain type of ring has outer diameter 58 millimeters. So there's your ring here. You can see this ring. And there are two circles in this ring. So you've got an outer diameter and you've got an inner diameter. These two circles, they're concentric circles. They've got a small diameter and a big. So the outer diameter is 58. The inner diameter is also given. It's 40. So you got the inner diameter is 40. Outer one is 58. And it's got a thickness. The thickness of this thing here from here to here is just 1 millimeter. All right. Now, so if one stacks enough rings on top of each other, so there you've got a stack here. You can see I've got a stack. Right? I don't know how many there are supposed to be here, but maybe that's a problem. Okay. But you know that each one is only 1 millimeter in thickness. So if there are 10 such rings, so then that means the distance from the top to the bottom will be 10 millimeters because you got one added to itself 10 times. Okay, so we don't know how many there are. Okay, it is possible to stand another ring vertically on top of the pile like this. So you can stand in such a way that the ring just touches the bottom. That means this thing here, it just we can't see it here, but it doesn't look as if it's touching the bottom. But this thing just touches the bottom. How many rings are in the stack when this happens? So this was the question that we were asking. We didn't know how many rings there are. So that's very interesting. Now you've got this ring touching the bottom. And so where does the geometry feature here now? The geometry features here because you see this point here, this thing just touches. This thing will be touching it at a single point here. And even here, you've got a single point where that is touching. And then the bottom of this ring is touching the floor. Okay, touching the floor. So let's see whether we can put this thing into a picture. It requires a certain amount of imagination. So what I'm going to do is I'm going to draw the floor, and I'm going to draw this thing here, which is just barely touching it. This thing is touching the floor. So I've drawn the floor first, and now I'm going to draw the circle. Or maybe I should draw the circle first. All right, let's put it out there. And now the circle, that's a ring there. This is the outer circle. It's touching the floor. So let me just put the floor down there. So there's a tangent here. All right. And then these two dots which I've drawn, there are 2 points on the circle, but they both are at the same height because they are both on the top rung. Right? So that means if they're the same height, this dot is here and this dot is here. And if you join these two, it now becomes a chord of the circle. It's a point. This line here is a line which joins 2 points on the circumference. That's called a chord. So this is the diagram that you've got here at the moment, right? And you actually know look, it's common sense. When you take this thing here and make it balance, these 2 points here will be symmetric. The thing will have to be exactly halfway between these two. So this actually is the diameter of the small circle. This is the diameter of the small circle. So which means that its length is 59. What is it? 40. Right. Now the question is, how many rings are in the stack? So we said earlier on, if there are X rings, right? If there are X rings, let X be equal to the number of rings. Each ring is 1 millimeter thickness. So if there are X rings, you have the height of the top part to the bottom is X, because it's 1 plus 1 plus 1, X times. So that height is X. So this is what you got here at the moment. And you also have, so they want to know, our problem is to calculate X. How do you calculate X? Well, we have to look at the center of the circle, the large circle. And see whether we can get some kind of an equation involving X. Okay? Now, what do we know? We know the diameter of the large circle, so which means that if I join these, this becomes the radius of the large circle. And the diameter of the large circle is 58. So that is now 29. The radius of the large circle is 29. Now, another thing is that when you join this to this point here, this becomes a tangent to the circle. And I think you should know that when you join the center of a circle to the point of contact of a tangent, it's perpendicular, it's 90 degrees. So when I join the center of the circle to this point of contact, I'm going to get 90 degrees. But we know that this is parallel to this, so this is also 90 degrees. We also know the full length of this, because this is 40. Now, yeah, you've got an interesting thing here, because you've got the center of a circle joined, is perpendicular to this chord, and there's an isosceles triangle sitting somewhere here, like that. See, isosceles, because these are radii, see. These two are equal, you got 290 degrees, you got a common side. These two triangles are congruent. This is the usual story about isosceles triangles. You know, if you got a perpendicular, it bisects it. So you got these two triangles are congruent, so therefore these two lines are actually equal. It's bisected. Right? The whole thing is 40, so each one will have to be 20. And now you've got a right angle triangle with two sides. This is 29 and this is 20. So if you call this h here, you got h squared equals 29 squared minus 20 squared. This is by Pythagoras. You got the hypotenuse squared minus this. And you don't have to use a calculator for this. This is the difference of two squares. 29 minus 20 into 29 plus 20. 29 minus 20 is 9. 29 plus 20 is 49. So h squared is 9 times 49. So h is 3 times 7. Isn't that beautiful? You don't have to work out what those big numbers are. So H is 27. So this is 27. And we're still trying to find X, but this thing here is a radius, you see. So this entire thing this is the radius of the circle. So your X is actually equal to X plus H, right? This X here plus H is actually equal to 29. It's the radius of the circle, and H is 27. I'm sorry, 21. H is 21. So X must be 8. So there were 8. This is 8. So that means that there were 8 rings in the stack. Beautiful problem. So much of geometry involved in this problem here. Circle geometry. Right? It's a theorem in geometry that if you join the center of a circle, if the center of a circle is perpendicular to a chord like this, then these two are equal. And conversely, if you join the center to the midpoint of a chord, then it's perpendicular. Because you can just use isosceles triangle to prove it. It's very easy to prove. So that's one of the theorems of geometry. The other theorem you used is that the radius of a circle is perpendicular to the tangent at the point of contact. Right? So we use that theorem. So 2 circle theorems we used. And the rest of it is just coming from this figure. Okay, so that is the solution to that problem. Okay, this last problem, I just put it in here, but you haven't thought about it. So maybe I'd better not do it. It's already 5 minutes to 7. But if you want, you can sort of record it. It's problem number 12, I think. You can try it. This is problem number 12, session 7. You have all the questions. I've given you the full set of questions in the problem book. So you look at session 7 of the seniors, look for problem 12, and you will find this question. Right? You can try it. It's an interesting question. Not very easy, but it's got a lot of nice geometry in this. Okay, and just ignore that pi. I don't know why pi is featuring and showing off there in the corner. Okay, so I was supposed to do this, but we got no time for this. But if you want to try it and ask me any questions on this thing here, I'll be quite happy to answer. This is my email address. You must always feel free to ask me any questions. I might not answer it straight away, but I will try to do it. Try to write down the solution and send it to you. So if you got stuck with any problem anywhere, you're quite free to call me. I don't have a problem with that. Okay, but although I lead a busy life, I might not be able to answer you straight away, but I will answer you sooner or later. Okay, guys, thank you very much for your patience, for being here till the end, and allowing me to indulge and take 27 more minutes of your valuable time. All the best and good night.